All right, this lesson is going to be on refraction. Last lesson I talked about refraction. Rather, I just mentioned the name, but I didn't even talk. I didn't even describe it in detail. But this lesson today, this lesson in this video is pretty much only on refraction. Right? We're only going to be talking about refraction. And so in this GIF that you see right here, uh, it's a, it's showing you the phenomenon of refraction. Right now, you can guess what's happening. So there's a light wave coming in. It's passing through a border, right? It's passing through something, and the direction of the light wave changes. The direction of the light wave changes. So that's at the most simplest explanation. This is what refraction is: the changing of the direction of a light wave as it passes through a medium. We're going to talk more about what the definition actually truly is later on, but this is just a good intro. And before we talk about refraction, I kind of want to discuss the two types of waves again, right? Mechanical waves, they require a medium to travel through. For example, sound. Sound requires air, right? Sound requires vibrating air molecules to transfer. And water waves require water. Electromagnetic waves, on the other hand, don't require a medium. For example, light. Light waves are electromagnetic waves, X-rays, ultraviolet rays, infrared rays, right? Radio waves. They're all electromagnetic waves and do not require a medium. Now, this video talks about both types of waves, but you can watch this on. You cannot watch this on YouTube. Or rather, I can't upload this video and show you that video clip at the same exact time because copyright issues, right? I tried. You can only upload a maximum of 2 minutes of copyrighted uh, videos before the video is blocked. So you guys are gonna have to watch this somewhere else. You're gonna have to watch the first video at this link right here. Right? So Vimeo doesn't have copyright issues, so you can watch it there. It's actually a fairly short video, fairly short. So Edpuzzle is going to stop at this point in time, so make sure you watch this video. Now, assuming that you finished the first video, you need to watch another video. This is the second video, okay? You have to watch this video at this link right here. Now, as light travels through a prism, light separates. Well, this is a summary, right? This is a summary of both videos. Assuming you've watched both videos, I'm gonna summarize it. So, as light travels through a prism, light separates into multiple different wavelengths and colors. So this is another property of refraction, right? Now you kind of, this also falls under the category of refraction. So now we're diving a bit more into it. So why does this happen? Why is it that when light travels through something, the wavelength changes, right? Why does light separate into multiple different wavelengths? So this is another phenomenon of refraction. So I'll let you watch the GIF entirely first. So you have a coin at the bottom of this cup, right? There's no water in it. And now you pour water into the cup. Originally, you couldn't see the coin. But now that you added water into the cup, you can now see the coin. And so why does that happen? Why does that happen? It's the same reason that happened in the videos that you watched. Light rays, light waves, as they go from one medium to another, the light bends. For example, as the light goes from the water into the air, light is bending. And so that's why you can see the coin at the bottom. It's because light is bending as it goes from the water to the air. All right. So that's basically what refraction is. And this is summarizing what you see. So let's look at the right hand image right here. Right, let's say you shine a light wave and the light wave is going this way. Right, the light wave is going this way. And then as it goes from the air into the water, what happens is that the light wave bends. It slows down. It slows down because water is more dense than air. And so the light wave bends, right? And you can finally see the coin that's up here, that's down here. That's why you can see the coin when there's water in it rather than when there's no water. All right, let's move on. And also, this is called, again, this is a refresher, this is called the angle of incidence. This is called the angle of incidence, and this right here, 40.6 degrees, is called the angle of refraction. The angle of refraction. So now let's talk about the index of refraction. So on the second page of your reference table, there should be a table called absolute indices of refraction. And so it says the frequency at 5.09 times 10 to the 14 hertz. You'll realize that by looking at the electromagnetic spectrum just above that table, that this is the frequency for light in between green and yellow. So maybe green or yellow light. This is for green and yellow light. And these numbers right here is basically saying how hard is it for light to travel through each of these materials? And the higher the number, the slower light will travel in these materials. The slower light will travel through each of these materials. So in air, you have an absolute index of refraction of 1. Well, if you try shining light into corn oil, light is going to travel a bit slower because the index of refraction is now 1.47. So it's basically the more dense the material, the harder, the slower light will travel in these materials. All right. So the higher the index of refraction, the slower the speed of the wave in that medium. And that is the reason why, well, when you travel from air into, let's say, water, for example, which is water has an index of refraction of 1.33, well, the light is going to bend. It's bending because the light wave is slowing down, just as what's being shown in this GIF right here. The GIF is not entirely accurate about the exact properties of refraction, but it's good at showing you, uh, it's good at showing you maybe why the light wave bends. Also, if you see something here, if you notice something, if it's going from air to water, you'll see that the wavelength decreases because the speed also decreases, because the formula speed is equal to frequency times wavelength. Your frequency of the light traveling through the medium is always going to stay consistent. It's always going to be the same. Let's move on. Can I move on? All right, cool. I actually want to talk about that right now. So, and now we get to the law of refraction. Right? So refraction is the bending of a wave as it passes from one medium to another. Right? And refraction involves a change in wave speed and wavelength. And here's the most important part. The frequency of the light wave does not change. It never changes as you go from another material into another one. Again, we're looking at the bottom right here. Just ignore the picture in the middle for now. V is equal to frequency times wavelength. Your frequency is always constant. But if your velocity is going down, then your frequency, then your wavelength must decrease as well. So that's basically what you're seeing right here. As the light wave goes from this medium to another, if the light wave is slowing down, well, you see that the wavelength gets shorter here. If you notice the wavelength in between this orange line and these blue lines, you'll see that the wavelength of this blue line is much lower, or rather not much lower, is shorter. is shorter than the orange wavelength. Now let's look at the image in the middle, right? Because this is the important part. This is how you answer the questions on that I'm going to ask you. So the light wave is coming from air, right? It's less dense. And the border, there's a medium here. So this part, this top part right here is air. And this bottom part right here is water. The entire bottom half of this side is water. And as the air goes into the water, well, water has an index of refraction of 1.33. In air, the index of refraction is 1.00. So if it's going from a lower to higher index of refraction, you know that the light wave is slowing down. Well, if the light wave is slowing down, well, this wave right here should come down right here. And so the angle should be lower, right? The refracted ray bends towards normal, so it goes this way. And you can see that if you're getting slower, then your wavelength must also get shorter, which is exactly what you're seeing here. All right. Now let's look on the image on the right hand side. So oil is more dense, and let's say this is corn oil. Let's say for the sake of this example, this is corn oil. And the index of refraction of corn oil, as you can see on the right hand side on this table right here, is 1.47. And the light wave from the corn oil is going into water. And water is less dense than oil. And the index of refraction is 1.33. That means you're going from a higher to lower index of refraction. Well, if that's happening, then the speed of the wave speeds up. If the speed of the wave speeds up as this light wave goes into water, goes into this water now, it's going to speed up and it's going to bend away. It's going to bend away now. And the wavelength of each light wave is going to increase as well. Right? So you can see this arrow rather. So on the left-hand image, you can see as the light wave goes from air to water, the light wave bends towards the normal line being the middle, the dashed line, right? The dashed line is the normal line because the light wave is getting slower. But if the light wave goes from oil to water, the light wave gets faster. So it bends uh, away from the normal line. So this part, this is one more slide. This is very important to the questions you're going to have to answer. So you saw in the part, let's say this is air, right? N1 is air and N2 is water. And so this entire bottom half of this screen is water. And above it is air. And so as the light wave, the incident wave, right? We call that the incident wave. The angle of incidence, again, remember, angle of incidence is this right here. The angle to the normal line. The normal line being this dashed line, which is perpendicular to the boundary, the medium boundary. So as the light wave comes in, it bends, it slows down because it goes from air to water. Water is more dense. And so this is the angle of refraction. Right here, this is your angle of refraction. The angle of refraction is this angle from this line right here to the normal line. So that's your angle of refraction. And remember, the angle of reflection is always equal to the angle of incidence. Remember this. Angle of incidence is equal to angle of reflection. So as this light wave comes in, there's an angle of refraction, light goes downward, and part of that light is reflected. Part of that light is reflected. It's very important to answering questions. All right. And I'll leave you on this page.